Is the NEET Odisha 2019 from Waves Concept. Question is like this. A tuning fork with frequency 800 Hz produces a resonance in resonance column tube with upper end open and lower end closes by water surface. Successive resonances are observed at lengths are given for us. What is the speed of the sound in air? So to solve this, first of all we shall know how does that resonance column operator works. Resonance column apparatus is a open tube or a open pipe. What do you mean by open pipe is it's one and half of it, a part of it is filled with water. There is some experimental arrangement. I'm not going to that. So this is considered like a closed end because water is there. But this end is open to atmosphere. So this is called open end. So this kind of pipe is called open pipe. So when air passes into this tube, the first possible way of air going is going this way and comes this back, right? So this part of the air has some frequency. So when you use a tuning fork, by varying the position of this air column, we can vary this air column length. At a particular length of that air column, which is called, this is the length of that air column. Frequency of the air column becomes equal to the frequency of the tuning fork. Then they comes in resonance and they together vibrates with a large booming sound. Then we can confirm that the resonance is happened. So what we can say is at first resonance, that is in this way this happens in the closed pipe. Of course this is actually water. Sound goes this way and comes back this way. So this is the formation of a node. This is the formation of an antinode. So you know the distance between node and antinode is, say, in a stretched string, stationary waves are formed. These points where displacement is minimum called nodes. The points where displacement is maximum is called antinode. So if you notice, this is only half the wave of this remaining part. This is not there. That part of the wave is not there. But if you imagine that part, and if you imagine that part, this total length is equal to lambda. This total length of the wave is wavelength lambda, because this is a complete wave. Now this second part is not there. So the length of this segment is only half of that. That is lambda by 2. This is called a segment whose length is lambda by 2. But now this is an antinode and node. The distance between them is even half of that lambda by 2. That's why the length of this stretched string equal to lambda by 4. L is nothing but equal to lambda divided by 4. That is fundamental mode of first resonance happens. And if you proceed further, the second resonance also happens. At second resonance, what do you mean by second resonance is simply we will lower this water column, so the length of the air column increases, and we repeat the experiment somewhere, so the air column gets reflected in this way. And again, when the frequency of the air column equal to the frequency of the stretched string, resonance is heard. In this case, here is a formation of a node, here is a formation of a node, here is a formation of antinode. Between node and node, length is, as I told you here, lambda by 2, like this. Between node and antinode, the distance is lambda by 4. So the entire length of that air column now becomes lambda by 2 plus lambda by 4. 4 is the LCM, 2m the plus lambda. 3 lambda by 4. You call this as first resonating length. You call this as second resonating length. So when you make L2 by L2 minus L1, it becomes 3 lambda by 4 minus lambda by 4. That is 2 lambda by 4. That is lambda by 2. From here we can write lambda as 2 times of second resonating length minus first resonating length. Velocity of a sound can be written like V equal to n lambda. Na? So n into whatever may be the lambda value, 2 times of L2 minus L1. So I have done all this to derive this formula. If you know this formula, you can directly come to this point and look into the data further. Let us substitute the data now. What is available for you? N is given for you in the problem as 800 Hz. L2 is 31.25. L1 is 9.75, both in centimeters. So I have to convert them into meters. That is into 10 power minus 2. So minus 2 and these 2 zeros will go. So 2 into 8, 16. 31.25 minus 9.75. You calculate, you will get 344 meter per second. That's a normal range of sound. Any of the other values are not actually velocities of sounds. Even if you have not solved this problem, you cannot opt any of the other answers, because in a room temperature, velocity of sound is around 340 to 350 meter per second. Anyway, this is the concept that I have explained to you. So while I am solving this problem, I have derived expression for the velocity of sound using resonance column apparatus, resonance experiment, and that's because there is a first resonance happens and resonance repeats at other length of the air column also. Now that concept, therefore, that will be helpful in understanding the things, right? Thank you for watching.